Our first speaker is Olivier Grisel. He is, I'm always saying that Olivier is a big contributor to Scikit-learn, and he does a bunch of other things, he's involved in a spin-off of Inria. Inria is one of the big contributors to Scikit-learn. I'm repeating Scikit-learn because there was this report that France made on AI, and I think that they completely missed Scikit-learn. But yeah, if you use Scikit-learn, you use partly French software, French-made kind of. So yeah, because they didn't mention that in the report, I thought it'd be good to mention it. But yeah, we're very happy to have Olivier here, and without further ado, please welcome Olivier Grisel to PAPIs.
Thank you. Yeah, my microphone is working. Okay. So hi everyone. So I'm a Scikit-learn contributor. I work at Inria as a software engineer, primarily on Scikit-learn, and also related stuff, related open source project basically. And today, so this conference is about managed hosted services for building and deploying predictive models. And today I would like to do the opposite. That is to set up your own infrastructure from scratch, just using open source building blocks without using any service provider. So I will focus on Dask, JupyterHub, and Kubernetes. So Kubernetes, how many of you have know what Kubernetes is? So half, a bit, yeah. So it's basically a cluster orchestration system. So a system for configuring the deployment of services and applications on a cluster, on a distributed setup. It's based on containers, like Docker containers. It makes it possible to manage distributed applications with several replicas, and also to schedule batch processing jobs that happen in the background on the same cluster. And they can share computer resources, but also persistent storage. And there is some kind of access control system based on role definitions. So it's a bit like an operating system, but for a cluster, an operating system for several machines. And finally, you can deploy this on premises on your own machines if you set it up by yourself. Or you can also provision a pre-installed Kubernetes cluster on all the major public clouds. So in this presentation, it's going to be mostly about how to use Kubernetes, and it's going to be mostly about demos. So the first demo, actually, it's I wanted to see here. I will introduce how to use to use Dask and JupyterHub on Kubernetes, and I will introduce what is Dask. So here, nope, not this one. This one. So this is my laptop running the dashboard, the Minikube dashboard, the Kubernetes dashboard. Running on the Minikube system. Minikube is a way to set up a small Kubernetes cluster for deployment, for testing and deployment on your machine. Does it run? Doesn't run. Okay. And basically, you can see that here I just have two services running. One is called Hub, and the other one is called Proxy. It's basically the JupyterHub that has been deployed. So JupyterHub is a HTTP interactive interface that makes it possible to give your users access to their own personalized interactive environment for data science. So in particular, you can configure JupyterHub to use a user management system such as GitHub, for instance. You could log in with your GitHub credentials or Google or OAuth, or you can plug it to your own IT if you want. Once you log in, you get access to your own JupyterLab environment. So here in the small terminal on the bottom, you can see that I'm also running in the background a command line command to access Kubernetes directly and to see what are the programs, the list of programs running on my cluster. So here I have JupyterHub, the proxy, a reverse proxy, and my JupyterLab session, my own personal interactive session that has been opened when I log in. It has been provisioned dynamically. So in this Jupyter Lab session, I have a notebook, and I will show you how to use Dask to basically to execute computation on that Kubernetes cluster. So Dask has some integration with native integration with Kubernetes. It can talk directly to the cluster. Dask, you can see it as an alternative to Spark, for instance, that is pure Python. And it's also better integrated with NumPy and Pandas. So if you want to do linear algebra computation, it's very nice. And it has also some machine learning tools. So if you use the kube cluster from Dask Kubernetes, basically, you can get a client object in Python that will talk directly to the Kubernetes cluster. As soon as you start it up, you get basically a scheduler process that is running. And there is a dashboard page dedicated for that scheduler that is already provisioned in the background. So I just had a problem with my port forwarding here, so I restarted the port forwarding. Then you should get your dashboard up and running and see what is happening from the Python point of view on the cluster. What Python programs are running on the cluster. So here at the beginning, there are no workers running. But I can dynamically ask to have at least 2 Python processes, minimum, and a maximum of 4. And it's an adaptive scheduling that will depend on the load, how much compute I need in my program, in my Python code. And so when I click Adapt, you can see here at the bottom that in Kubernetes, automatically, there are 2 new workers that have been provisioned, 2 new pods running in containers. They automatically show up here, they are registered in the Dask scheduler automatically, and you see that each of them has 2 cores, 2 threads. So in total, for this small laptop cluster, I have 2 workers, 2 Python processes, and each of them has 2 cores. If I switch back to the status page on the Dask scheduler view, I see that there are 80 megabytes allocated for my Python process on the cluster. It's just the empty workers with no data loaded so far. And you see that they are not doing anything. There is no task scheduled so far. So once I have this, I can define regular Python functions. So here, the first function is called inc for incrementing x plus 1. But I make it slow by importing random and sleeping a random time so that we can see the execution happening if it's not too fast. So we define in the increment inc plus 1, the function double the value of x and return it, and then a function that takes 2 arguments, add, that does an addition of the 2 of them. So those are regular Python functions. If I execute them in the Jupyter notebook, I just get the answer directly. But I can also use my client object to talk to the cluster and to submit the execution of the inc function on the cluster by providing some arguments, some input data. So here the input data is just a single integer, it's 1. And when I get that, instead of getting the result back, I get a future object. It's just a pointer to the result of the computation. And you see that by default, I have a unique identifier for fetching back the result. But by default, it's in status pending because it has just been scheduled. But if I refresh the state, it's very fast to execute. And you see that now it's in status finished. Because it was very easy to compute. The result was still on the cluster, but then I can fetch it back into my Jupyter environment by just calling the result method. So it's just a way to schedule work on the cluster and not fetch back the result directly, because then I can put some more dependencies between the tasks. And this is an example. So here in this example, I define a loop over integers. And first, I will increment the integer by calling a first times the submit function with the increment method. Then I will get the result of that first increment and pass it to another function that will double it. And then those 2 intermediate results, I will combine them by an addition to get a z. And I will collect all the z value, the z variable value in a list. And at the end, I will compute the sum of all the values. So, and store that in a variable that is called total. If I do that, if I execute the cell, you can see that many of the operations can be parallelized. So all my 4 threads are being used in parallel. And because I have set it up the adaptive computation, you see that there are additional workers that have been provisioned dynamically on my Kubernetes cluster because the load in my scheduler queue was increasing. And that speeds up the computation. And as soon as it's complete, because I said that I want just a minimum of 2, maximum of 4, automatically at the end of the computation, it will release the compute resources that I don't use anymore. So if I switch to the graph tab here, you can see also that I see the dependency between my tasks, and I see in green the stuff that is processing. In blue is the stuff that has been already computed, and the intermediate results have been already reused, so we don't need to store it anymore. In red, we have the intermediate results that might still be useful for some other task in the future, so they are kept in memory on the cluster. So you can see that the memory usage of the cluster can increase over time because there are some intermediate results that are stored on the workers that stay there because in your interactive session later maybe you might need them. And this is depending on the local variable scoping of the main program. So automatically you see that the 2 workers here have been released. The 2 additional workers that were dynamically provisioned, they already have been released. And so those resources can be shared with other data scientists. We maximally share basically the compute resources very efficiently. I don't know what it's stopping now, what I was supposed to do. So yes, here you see those red values here are the values that are stored in the cluster. Those corresponds to the total variable in my program and the list of Z that I can potentially reuse later in my program. So here, instead of just computing the sum by doing a full sum of a list, what I can do is do a more efficient operation, which is called all reduce in HPC language, which is basically doing a tree reduction for the sum operation, an aggregation that will happen locally first between nodes, and then the intermediate results are aggregated, so that the communications between the nodes is not too high for a single node. And we can parallelize most of the aggregation operation itself using a tree structure, a tree dependency between the tasks. So this can be written in regular Python using a while loop that will call add on 2 leaves of that tree and progressively storing the result and putting it back in the list of intermediate results. And as long as I have some intermediate result, I keep on aggregating recursively like this. If I execute this cell, automatically you see the tree structure, the dependency that appears in the scheduler, and you say in green that some operations are already being scheduled and executed in parallel, and progressively it will compute everything. And you see here my 2 workers, my 2 additional workers, the adaptive workload has been provisioned and accelerates the computation on the go. And finally, I have my final object that stores the result of the sum. One more thing to say here is that here in my Python program, I have some variables that point to the intermediate result here. If I delete those variables here, they are no longer needed in my program. So automatically, Dask tracks this and will release the memory allocated on the cluster because those intermediate results are not used anymore. So there are still some variables somewhere in my program that has some dependency. I think it's the previous total computation that was still there. But as soon as I delete stuff here, automatically it frees the resources, the memory resources in the cluster. And furthermore, if I shut down my program here, if I restart the kernel here, restart kernel, yeah, click, automatically the workers that were allocated for this computation are terminated because they are not needed anymore. So the resources is shared efficiently with other data scientists that might be using the cluster. So this was the first demo. I have a second demo that is more about machine learning. I will do it right now, using scikit-learn. So basically, you're using the same primitives on the same compute infrastructure, but this time we're going to use scikit-learn. So here again, is it running? Yeah. So here again, we set up Dask to communicate to the cluster as we did previously. Doesn't seem to run. Okay. So I set up the cluster connection. I allocate some workers. This time I decide to set a fixed number of workers, and they will stay there all the time. You see, they are very quick to provision. Because the image of the container is already there on the cluster, so it doesn't need to download any virtual environment or whatever. It's already there, so you just need to start the workers. It's very fast to start up. So I have my 4 workers. Each of them has 2 cores, so 8 cores total. So now I'm going to use Scikit-learn and JobLib. So by default, Scikit-learn for parallel computation, it's only able to do single machine parallelism. For instance, if you do a random forest, you can train different trees in parallel. It can use either threads or multi-processes. And this is done by a component that is called JobLib that is embedded directly in Scikit-learn and that manages the threads and the processes. What is new in JobLib in recent version is that now you can unplug the default multiprocessing backend and make it talk to some external compute infrastructure like Dask based on top of Kubernetes, for instance. So here in this example, I will do some traditional machine learning experiments. So I will generate some classification data just for the demo. So just 1,000 example. We'll train test splits to have a test set for the final evaluation. And so here, this is just 10-dimensional data or 20-dimensional data, something. And it's a binary classification test. It's just a synthetic toy experiment. So I want to train a machine learning model in parallel. So here again, I have my my problem with my port that has been. Okay. So here I'm doing training support vector machines, but I don't know which hyperparameters are the best. So I will run a grid search to find the best hyperparameters between 2 different kinds of kernels, different value of the regularizers, the bandwidths of the kernel. And I will just import from Scikit-learn the regular tools like support vector machine SVC and grid search CV. That's our regular Scikit-learn components. And if I would run the grid search traditionally, I will just call grid search.fit on X train and Y train, and that would run on possibly several cores, but on a single machine, not on the cluster. It will try to fit models for all the possible combination in that grid, and this is an embarrassingly parallel task, so it can use many cores or many in parallel. Here, I don't want to use my local machine. I want to use the cluster. So instead of running grid search fit X train, Y train, I will use Dask-ML and the JobLib ability of JobLib to talk to Dask to run on the cluster. So maybe I can move a bit forward. So this is what is written here. Here, I have the same line as previously, grid search fit something, but previously I just import JobLib and I wrap that line under this JobLib parallel backend Dask. Basically, I said JobLib use Dask whenever you are below this block, inside this block. So do not use your traditional threads, use the cluster instead. And if we execute this, automatically we'll see that everything is scheduled on the clusters. At the beginning, there is some deserialization that is happening to load the data in memory. And then it's running very efficiently in parallel. And you see that the tasks are streaming on the fly. Scikit-learn is dispatching new stuff to do. And this is sent to the Dask cluster and being run in parallel. And the result of the evaluation of the models are collected so that then we can introspect them. And you see, so it's running on all the workers. So the results are in an attribute of the grid search object. This, I can wrap them in a pandas data frame to be able to sort and to display them as a table in the Jupyter notebook. So here we sort the results by the best mean cross-validation score across the different folds. So the best one has 95% accuracy. And we can see what are the values of the parameters for that model. So it's a RBF kernel model with a gamma of 0.01, C is some value, and you see that other models with different parameters have different scores. And here the different columns is for each individual cross-validation split, we have all the values. So this is traditional grid search. The only difference is that we plugged it directly to talk to Dask. And then I get my best model. I can run some prediction on the true test set that I haven't used so far and compute the final test evaluation score. I see that it's 95%. It's approximately the same as the cross-validation score, so everything is fine. So this is nice. The only limitation here is that we are using traditional scikit-learn directly, and scikit-learn has been written to use NumPy and pandas as input data structures. And so it means that scikit-learn expects the data to fit in memory on a single machine. So if your data is larger than this toy data set that I used here with just a couple of thousands of samples, in today's machine you can fit several gigabytes of data in RAM, so it's not that a limitation in practice. But if your data doesn't fit on a single machine because it's too large, then this simple use of scikit-learn, even if you use Dask, will not cut it. So what you need for running on large data that doesn't fit on a single node on the cluster is some algorithm that is able to stream the data directly and is able to use an input data structure that is not completely materialized in memory on a single node. So here we are going to use Dask data structure instead of NumPy. And to do that, we are going to use a machine learning library which is called Dask ML, which is basically some kind of wrapper of scikit-learn, but it's reusing internal building blocks, primitives of scikit-learn, but it's working with different kinds of data structure. And one of them is the Dask array, which is basically a chunked NumPy array, where each chunk is stored on a different worker on the cluster. And it can be fetched lazily from the data source, from the disk, from S3 or for a database. And basically, it's just a logical representation of a very large array that wouldn't fit on any of the machine. And you see that there are, I think, 10 million or 100 million. I think it's 10 million records, and each chunk has 1 million records. The total is still very small. It's just 100 megabytes. But this data structure is chunked now, so it can be made scalable to many machines. But because I'm running a small demo on my laptop, I didn't want to try on a terabyte of data. So now that we have this data structure, we need algorithms that are able to work in parallel on all the chunks, and we also need a specific implementation that accepts this kind of chunked arrays. So here we have in DaskML, for instance, for clustering, we have the k-means algorithm. The only difference with the traditional k-means algorithm is not using k-means plus for the initialization. It's using k-means parallel, which is some kind of approximation that runs in parallel on different chunks. And so this has been implemented in DaskML, and we can try to use it on this chunk data. So if we execute it, we can see that this has many intermediate steps. So you see different colors for all the different operations. The red here is for communication of the initial data to the nodes. And then you see the task for the initialization, the k-means parallel initialization. And after this first step of dispatch of computation, we have the true k-means algorithm that is also can be also be computed in parallel. And you see that from time to time you have a vertical line where there is nothing happening on the workers. It's basically intermediate results that have been fetched back to the driver program, and the driver program will compute some aggregate statistics and send back additional a new iteration of the algorithm that can be chunked into parallel operations. And here you see also each of the individual tasks, and you see the iterations of the algorithm. For each iteration, you have a batch of tasks that have been deployed here. So at the end of the convergence of this model, what is interesting is to see the profile tab. So here again, I had a problem with my network, so the profile tab was slow to display. But you can see that the attribute label here is actually not a NumPy array as would have been the case in scikit-learn. It's also a Dask array. It means that the results are not materialized back to the driver. They are still on the cluster and can be lazily fetched upon request back to the driver if we need them. If we don't need them, there is no point in fetching them back ahead of time. They might be big, so we keep them on the cluster. But if we want to use matplotlib to visualize the label of the clusters, what we can do is just take a subsample. And subsampling is just a slice object that we pass to this Dask array to fetch just a subsample of elements and do visualization of that. So it's much more efficient. We don't need to fetch back all the results. We can just fetch very efficiently a small subsample. And finally, I think my profile tab works in the end. I will just skip forward. Yeah. Just here. On the profile tab, what is interesting is that you have a timeline of all the execution that I've seen been executed in the past. You can see the CPU usage at the bottom. And you can select a chunk of that timeline. So for instance, here, that was the first computation that we did with the support vector machine. And here you have a flame graph to see which functions were expensive. So here you can see that most of the time during that section was spent in the dense fit function from libsvm that is used internally in scikit-learn. So fitting the support vector machine model was what was important. And it's being called by support vector machine, by cross-validation, by joblib. You can see the stack of call naturally in that view by going down. And here you see that there is another operation that takes some time. So it's actually computing the prediction for the support vector machine to compute the cross-validation score. And so you can see the ratio between fitting and predicting. Here, if I move below in the timeline, I see the initialization of the k-means parallel algorithm, and I can see which function in Python have been called, so completing Euclidean distances. And here I select another block, and it's actually the final convergence of the k-means algorithm, and you see that it's computing pairwise distances and taking the mean value to the closest centroid in that space, which makes sense, which is the cost-sensitive operation in k-means. All right, so I think I'll stop here for the demo. So I don't know the timing.
We have time for questions.
Okay.
We always have time for questions. That's one of the things that we want to make different from some other content. But yeah, time for questions. While we take questions, we might need to. Our next talk is actually a demo involving some exotic hardware. Do you want to start setting up, or is you're fine? Okay, cool. Let's go with questions. Someone raised their hand.
Yeah.
You want to go?
So just there are some references if you want to set it up. Yeah, some documentation and the slides and videos have been tweeted on my Twitter.
Hi Olivier, thanks for a nice talk. So how would you compare Dask with PySpark, which is kind of the dominant platform, and now it has Kubernetes native support since 2.3?
Yeah. So since the last version of Spark, you have also the same kind of Kubernetes integration that I demonstrated for Dask. The main difference, Dask is pure Python, so it's more lightweight to install, to set up on your machine, just using Anaconda. If you want a single machine operation, it's very easy. And so the same program is very easily scaled down back to one machine, to the single machine. So for debugging, you can use the regular debugger from Python, which is not necessarily the case with PySpark, because you have a sandwich of Python, Scala, scheduler, and Python workers, which makes it harder to understand when you are just a regular Python data scientist with no Scala expertise. If you're a Scala developer, I think Spark is very nice too. There is another difference, is that Dask has more as a Dask array data structure for n-dimensional arrays, like general NumPy arrays, which is very good for people working not necessarily with tabular data, like data frames, but with geoscience data, for instance. And there are also libraries like Xarray, which is some kind of generalization of pandas for n-dimensional data, and that is very useful for geoscience people studying climate change, for instance. And there is actually a demo of this on pangeopydata.org, which is basically the same kind of setup with JupyterHub that I've demonstrated today, but with PyArray and plugged on the Google Cloud infrastructure. And you have access to geoscience data, and you can see the kind of workflow that you can use in that case. So I would say it's more versatile towards more general computation and not just necessarily traditional tabular data science. No question.
Amazing presentation, thank you. Can I ask another what's the difference question?
Yeah.
What's the difference between Kubernetes and Docker Swarm?
So Docker Swarm is basically the orchestration layer for Docker that was developed by the same developer as the Docker container itself. So basically Kubernetes was implemented by other people, initially by people from Google, but now it's a very wide community, open source community of contributors. It's just that the adoption of Kubernetes was much faster than Docker Swarm, I would say. Nowadays, I think even the Docker company, they are providing Kubernetes as a service. Manage Kubernetes. So I think it's just in terms of adoption, Kubernetes was faster to pick up a very large community, and maybe it was ready earlier to be production ready compared to Docker Swarm, which maybe took more time to be in a stable position. But they are very similar. Docker Swarm and Docker Compose might be easier to use from a developer point of view. They are easier to learn. Kubernetes to set up, it's maybe slightly more complex, but it's also the feature set. There are many plugins for different kind of storage, different GPU support, whatever. There are a ton of stuff, and they are supported with all the major clouds, and by default by Google Cloud and Azure as hosted services, and I think Amazon is going to provide this also.
Any other questions? Let's sure I saw a couple of hands over there. No, you guys getting shy or? Yep. Yes. Okay, I might ask one. What's so in the sort of idea of making these things easier to use? What's coming next, according to you?
To set it up, it's kind of complex. It could be made easier, but if you use hosted services like Google, it's already quite easy. Something that I didn't show here is that I just demonstrated interactive setup, which when you train model, you should not do everything in a Jupyter notebook because for maintenance is really not a good idea. So if you want to do a batch training of many models on a regular basis, it might be better to use a batch processing system. And if you want to do that with Python and Kubernetes as the compute infrastructure, you can use open source project like Polyaxon, which is quite new also. I haven't had the opportunity to use it extensively so far, but have a look at this. It's just a command line interface, a bit like a Floyd Hub, but that you can host yourself, basically. Where you can define in a YAML file the parameter of a grid search, run compute on GPUs using TensorFlow, PyTorch, whatever, Scikit-learn if you want. And there is also Kubeflow, which is the similar kind of setup. It's more for interactive development, I think. Using JupyterHub and TensorFlow together, it's packaged in a specific way. So I think it's more like the open source developer community is slowly integrating Kubernetes and making it a native component of all those libraries. Like we said for Spark, it was since the last release. Now with Dask, it's also integrated in this Dask Kubernetes component. And I think more and more projects will naturally work on Kubernetes rather than working on a single machine.
Cool. I think we actually have a couple of more open source machine learning related talks that mention usage of Kubernetes. That should be today. Seeing Google Cloud just reminded me that we were supposed to have a Google Cloud tutorial, but there was an issue with the speaker coming to London. Actually, quite a few speakers have had issues coming to London, visa issues and other issues. I'm not sure what's going on. But anyways, that's not happening. And there's a couple of speaker changes also. So there's only one talk so far that is being cancelled. It's the Google Cloud one. The other ones are still here, but there might be a couple of speaker changes. The last up-to-date information is on the mobile app. All right, let's thank Olivier for this great demo.